Hey everyone, it's Wilmer from the Game Academy. In this episode, let's revisit an old effect in Shader Graph. We created this simple force field in a previous series. This video adds a small update and makes the force field more interactive with some particle collisions. And now that's a little bit more like a force field. Just as a recap, our force field is a giant sphere with a custom shader graph. Essentially, we have a transparent base color plus a glow around the edges coming from a Fresnel effect. On top of that, we have this scanline that moves vertically in UV space. We multiply that with a more interesting pattern, a honeycomb of hexagons in this case. Some judicious post-processing then gives the scene a sci-fi look. Edit the shader graph to see how it's changed from the previous videos. This is still a relatively basic graph. I could have broken it down into subgraphs, but instead I've left the whole network intact and organized it with groups and sticky notes. The nodes are divided into several major branches like this. Each one represents a different part of the shader. In our output, our shader is set to transparent and double-sided. A base color fills the volume uniformly with a translucent albedo. This branch creates the Fresnel effect and edge glow. And there's also some animated Voronoi noise to help break up the intensity so it's not quite so static. Over here, these nodes contain the scanline effect. We pass the time into a tiling and offset to move the texture continuously up or down. Multiply by a fill texture to generate that hexagonal pattern. Then use some HDR color to make it glow with our post-processing. All of this should seem familiar to you if you followed along with the previous videos. Some nodes and effects have been reworked. The color ramps and electrical noise have been notably omitted from this version for the sake of simplicity. But new to the graph are extra properties and branch nodes allowing you to toggle each section on or off in the material inspector. Here you can select which parts of the shader graph to enable or disable. A script can address these as well if they're exposed publicly in the Blackboard. Our demo UI shows this in action. The toggle buttons invoke some custom events synced up with the material properties. In this update, we've also added this additional intersection where the force field touches any other solid geometry. We can achieve this with the scene depth node, which effectively gives us the camera Z buffer when the sampling is set to I. The raw mode of the screen position split out as an alpha channel gives us the vertex positions of the force field sphere. If you offset that by a small amount and then subtract it from the camera depth, the result is a thin interface where the force field touches everything else. Reverse this black to white with a 1-, and then we blend that with a smooth step and intensify its value to match the rim glow more closely. Add those together, and now you have a nicely defined boundary for our force field. To make our force field react to a projectile or weapon hit, we add this extra branch to our shader graph. We'll deform the force field mesh by offsetting its vertices via the position node. And this actually happens in 3 parts. To make the deformation fall off smoothly along the surface, we can use the distance node. Given a specific 3D point in space, we measure to each vertex on the model. If we subtract that difference from some maximum radius, then we can define a range of influence, clamping all negative values to 0, of course. You'll multiply this by a sine wave. That's the second part. We'll animate the effect so it's not just a static deform. Instead, this will give you a nice undulating ripple. And then up here, we'll define a direction and amplitude that you can use to control that wave-like motion. Multiply all these things together and you'll get a 3D deformation that can affect the mesh. Then our vertices can react when an event like a particle system collision triggers a response. External scripts can interact with the shader using the properties. And as such, it's good practice to use a naming convention in the reference fields on the Blackboard. That ensures that you can locate your properties more easily. In my case, I've chosen to use an underbar character in front of the camel case version of the property name. Whatever you choose, just make sure that it's consistent. we've created a Forcefield Impact.cs script to communicate with our force field. Here we have a number of methods that enable or disable the corresponding toggles in the shader graph, and that naming convention will come in handy here. In the apply impact method, you simply pass in a 3D point and a direction. Then we invoke the various set methods of the mesh renderer's material. That creates the displacement that makes the force field bounce. Then we can use the dampen method to make the displacement settle down. Dampen runs every frame, gradually reducing the amplitude. If something triggers the vertex displacement, the resulting wave-like motion will come to a rest by itself. For the purposes of this demo, there is a special demo weapon CS script. This simply controls a particle system via mouse input. Hold down the left mouse button to fire. A timer controls the fire rate, and raycasting through the cursor determines whether you hit a valid target. If you do hit something, then the weapon turns to face target, and it emits one particle and plays one sound clip. The effect looks like a glowing energy bolt with a trail renderer. A bunch of those fired in succession sort of looks like a laser blast. The collision module is the secret that allows us to interact with the force field. A particle collision event invokes every time one particle impacts a physics collider. To handle these particle collisions, we also have a custom particle collision effect script attached to the weapon. Inside, we get a reference to the primary particle system, and we also set up fields for secondary particles to spawn on impact. Unity invokes the onParticle collision method whenever a particle strikes an appropriate game object. Here we loop through a list of collision events and then spawn impact particles at each point of intersection. Then we align those collision effects with the normal direction at each point of contact. If the game object contains a force field impact component, we can pass the intersection and normal direction to drive the ripple effect on our sphere. Then we just need to clean up the collision effects particles using the destroy method. The result is a Sci-Fi energy weapon that can interact with our force field. And you can modify the force field impact's amplitude to make the force field bounce dramatically when hit with a large value or vibrate very subtly when struck with a small one. And now your force field feels more like a defensive barrier. If you want to jazz the effect up further, don't forget to add extra particle systems. A looping energy ring can help it feel more dynamic, but feel free to get creative here and make the effect your own. Of course, you'll need to replace the demo weapon CS script with a custom weapon script from your game, but if you're using a particle collision event, everything else should remain about the same. And now we have a visually functional force field. Okay, well, there you have it, building better sci-fi defenses through shader graph. To grab the example project, just go to our GitHub. If you want to support the channel, the video is part of a full lighting and shading course. Here you can learn about the fundamentals of lighting in Unity from a technical artist's perspective. See the link in the description for details. Okay, this is Wilmer. Have fun with those shaders. And of course, check back for more game dev updates, tips, and tricks. Until the next one, I'll see you in the Game Academy.